I'm going to go through this video and show you taking a simple two-dimensional plate that you've created in SolidWorks as a thickness sort of plate and saving it in SolidWorks and then uploading it to ansys for simulations. Here we are in SolidWorks, familiar tool that it is, and we have this rectangular plate. Now, in a previous video, we did the simulation of this plate, but for now, I just want to save the part itself, and I'm going to save it as a step file. And I'll call it heat plate and save it on the desktop. And I'm just going to minimize SolidWorks, but I'm keeping SolidWorks open and starting up ansys workbench. And here we have ansys workbench open up fresh, and we're going to do a steady state thermal simulation. We're going to start off by looking at the engineering data that we have to work with. And I want to view the outline and the table. And we only have structural steel at the moment. So I'm going to select the engineering library database and general materials. And I would like aluminum and copper. Hey, it's me again. So now we should have those in our model. And if I close that, our engineering data is added. I'm going to go to geometry, and I don't want to do a 3D analysis. I want to do a 2D. So I'm going to select the 2D simplification. And now with that, I want to import geometry, and I'll browse. And on my desktop, I should find that most recent step file. There it is, heat plate step. And that's present. So now I should be able to open that assignment. So I'm serious. It is an assignment, and you're going to want to do it. And so there we have the problem, which is because SolidWorks saved the step file as a solid, and the 2D geometry was expecting a two-dimensional part, I'm going to have to go back to 3D. And let's try that again. First of all, I'll update upstream components. And there we have the solid part from SolidWorks. The problem we have though now is that we wanted to do a two-dimensional analysis, but it's a three-dimensional part. So for a thermal analysis, we can solve that by providing boundary conditions on the faces to basically make them no heat transfer. The other way to do this, of course, would be to use a different CAD tool, which is the one built into ansys, that frankly I find really annoying because I'm not comfortable with it. But I'm comfortable with SolidWorks at the moment. So now in this case, we'll have to apply materials. And I want to use aluminum. And so I'm going to do a material assignment. I'm going to pick the body and select that and apply. And the material that I want to apply to it will be aluminum alloy. And there we have it. So we can see that it's got a check mark there by aluminum alloy assigned. Our next trick is to generate the mesh. And we can look at different generation options. We can look at the default sizing, for instance. The element size we're going to use as default. And we can pick that element size to be 0.5 meters. And there's the mesh, and you'll see as you scroll over it that the rough size of the mesh is shown by the circle that you scroll over. Now, if we're happy with that, that's fine. We can set up boundary conditions. So we select the steady state model, and you'll see, first of all, that there's boundary conditions, and we want to make perfectly insulated for this face and this face. Oops, we have to go Control Select. There, we've got the two outer faces are perfectly insulated, and so those are selected. And then we can look at temperature boundary. And we want to select by face because this is now not two-dimensional. And I pick that face and apply. And I'm going to make that temperature 0. Now I'd like to pick this opposite face for a heat flux. And so I'm still selecting face. Choose that, apply, and I want that to be 100 watts per meter squared. Now that is 100 watts per meter squared. The positive direction is inward in a heat flux calculation. So this is going to be a plate that will be getting warmer. Now the last two that I'll want to add will be perfectly insulated. I want to put that perfectly insulated on this top edge. And click Apply. And okay, so the assignment: round plate, 1 meter outside diameter, 1 centimeter thick, made of aluminum, and the heat generation that I described is going to first of all be a generation term of the body of the mass, and you can see how to do that in in ansys. And then I want to choose another temperature boundary, and I'm going to select that face and apply. And I'm going to make that 0 as well. And now if you click to the overall steady state thermal, you'll see that it'll summarize for you what the boundary conditions are that you've chosen. We've got boundary condition A, which is on both sides of the plate, top and bottom. We've got the heat flux out the right-hand side, which is B. We've got a temperature boundary of 0 at C. We've got a temperature boundary of 0 at D. And we've got a heat flow of 0 at E. So that covers off all the boundaries. In our solution, we'll select temperature. And we might also select directional heat flux, and then solve. So our temperature plot, which shows that the right-hand side is getting warmer while the bottom and the left are still cold because they're set to be 0, you can see that there's an interesting gradation. Now, the fact that it's only based on a small number of nodes is worth remembering, that in fact the nodes that we have are quite broadly spaced. So we can go back to the mesh and we can refine that mesh. Now if we look at the temperature, it looks the same, but that's because it's generally a pretty boring piece. So the next step in this is to make some changes to the SolidWorks CAD model and then rerun the simulation. And we can do that without without even jumping out of ansys. Let's see. So here we are back in ansys. I'm just going to minimize that. I'm going to minimize the ansys workbench and open back up my SolidWorks. Now with SolidWorks, I'm going to make an extruded cut on this face. I'm going to plunk a hole right here. And I think I'll do another hole here. Whoops. So now this has become a much more complicated structure. And I want to cut through both. There. And if I save as, and I'm still going to save it as the same name. And if I minimize that and go back to Workbench, I'm going to go back and update. And if I update geometry from source, you see that I've got this part that now has the holes in it that I created in SolidWorks. So you can continue to run SolidWorks as a tool, but now because we've changed this so much, we can go and so now we've reassigned the aluminum alloy to this part, even though nothing really had changed. And now we can generate the new mesh. And you can see that the mesh generation tool, the way that I've chosen it, has created some more detail. And if that's all done, our boundary conditions should be fine.
And then you can cut a hole in it, like I showed in this last video. And that hole you can put in there, make it 10 centimeters at the center of the plate, remesh, and see what the result looks like.
But they don't like our geometry. So we have to go back to the heat flow, which I selected on the basis of faces. And I selected that face and that face and apply.
You're going to be looking for a temperature gradient, and you're going to be doing not a steady state thermal model, but transient. You haven't tried that yet.
And so it went through the solution, it gave us a warning message. Let's see what the temperature looks like. There's the temperature plot again. And you can see that the holes made some difference in the temperatures, as you would expect they would. I should be more specific as to what those holes were for and what their temperatures might be. But the meshing would be required to more correctly model those holes. And I can look at the directional heat flux, and you can see that while the number of holes that I have around some of these, or the number of grid elements I have around some of these holes is fairly small, I'm estimating that there's a different heat flux on the top than the sides of the holes, and that to some extent makes some sense. But we can't trust this in the details yet because the mesh is too coarse. So that was a simple example showing you that you can actually go back and forth between SolidWorks models and running your ansys simulations. It's a little bit chunky in that you're going to have to reapply certain conditions in the model, So it isn't that slick, but it does work without too much pain. If you don't like doing that, then you can start to use space claim directly in ansys. And with space claim, you can actually make changes on the fly and export them directly to the model. But you're going to find that because you're so familiar now with working with SolidWorks, that really all you'll want to do in space claim are fairly simple stuff until you invest more time in playing with it. So that's it for now.